In any case, it's a great honor to have our first speaker of this semester, Professor Piotr Chrusciel from BIMSA and CTP in Polish Academy of Sciences, who talks about mathematical relativity, this and that.
So, good afternoon, everyone. I must say that I'm not on the list, so I couldn't sign. So, as you see here, I'm both member of BIMSA, but I'm also employed by the Center of Theoretical Physics of the Polish Academy of Sciences, where I spent part of my time. And before coming to here, I was at various places, but lately at University of Vienna for many years. So I was asked to introduce you both to my field and to convince you that I'm doing something important in my field. And that's a difficult exercise because there's a lot of important and interesting things happening in my field, about which I'm not going to talk because it would take half of my seminar, and then I wouldn't be able to explain to you why I'm good. So in particular, there are beautiful results by Yao about quasi-local mass or positivity of mass, which are one of the core developments in the field. There are beautiful results by Kleinerman about stability of black holes, Kleinerman, Sheftel, and Giorgi. And I'm not going to talk about these because I just don't have time to talk about everything here. So let me start by showing you one of my favorite science videos or simulations. So this is a journey into the center of our galaxy. Sagittarius A star is the more or less the barycenter of our galaxy, and this is the zoom when we go when we try to see deeper in the center. It's an animation, but based on real data. I think it's a fantastic animation where eventually, by many orders of magnitude of amplification, we get to the center of our galaxy. And this is now a movie of stars moving around the center of the galaxy. That's an extremely fast-forward movie. This movie, which takes a few seconds here, has been 30 or 40 years of data. Okay? So you look at the center of our galaxy for 30 years, you take pictures, and you can follow the motion of individual stars around something which is obviously sitting there, but which we don't see. Right? So this is what we think is the. Let me just run it once again because I think it's just so beautiful. So what you see at the end is not planets moving around the sun, which is bread and butter for astronomy, but there are stars moving around an object which we don't see in this spectrum in which this bandwidth, in which this movie was taken, and which we can feed Newtonian orbits and very well to determine the masses of the stars which are there, and this allows us to find out that the center of our galaxy, there's something sitting there which is 400,000 masses of our sun, and we should see it, but we don't. And a very good model which explains this is a black hole sitting there. Of course, that doesn't prove that there is a black hole sitting there, but this is our best explanation of what we see here, right? So these are stars which move around this object on orbits which we can very well explain by our physics. So this is Sagittarius A star, and so this is about black holes. And well, one of the key theorems in mathematical relativity, to which I have contributed quite a lot, and that's why I want to start with this result, is about uniqueness of black holes, right? So we have of course, black holes are, there isn't one black hole in a model because black holes are dynamical objects. But once we think that many of them, or maybe most, or maybe all, will settle to a single black hole which is time independent, and then we want to understand them. And so this is called the theorem black holes have no hair. So that just can be explained by very simple arguments. And the theorem says that if you have a stationary black hole, electrovacuum means that either it's vacuum or at most Maxwell fields. And now there are these funny hypotheses which I don't like, and I'm going to say you more about them, and that's why they're in red. So if you assume it's analytic, if you assume it's connected, it satisfies some regularity conditions, and then it should be a black hole which has been written down explicitly. In the vacuum case, this is a solution due to Mr. Kerr, and the charged version is due to Kerr, to Newman. So essentially, it's a theorem which tells you that, which is supposed to tell you that black holes are unique. Right? They can be uniquely characterized by Kerr-Newman actually are parameterized by one mass and the direction of rotation. So and the length. So one vector, which is the spin, and one mass, 4 parameters. So the belief is that stationary objects in the universe, which are black holes, are described by only 4 parameters, which is an amazing property. I mean, things in physics tend to be complicated and described in many parameters. Right? So here, there should be only 4. And indeed, we are at a stage where we can test this by observation. Right? We can look at stars and test whether they are at candidate black holes in the sky and test whether they have the right properties. We are getting to this degree of precision. Now, well, the inner structure, well, inside there is singularity and all terrible things can happen, but when you look at it from outside, you just see something described by 4 parameters. Doesn't exist from outside. Maybe there's a lot of, I mean, a black hole is something that you cannot see what's inside, right? That's the problem. Right? So there might be a lot of structure inside, but if you're looking at it from outside, you only see spin and mass. Right? So this is an amazing result, and now is it a result, right? Because first you are assuming that it's analytic and connected. So connected means there's only one black hole, right? So that's okay. There could be configuration where several ones, and that's a different story. But to assume that it is only one, so there is no black holes very far away from this one. And there is this curious hypothesis of analyticity. Now, I mean, here we are mathematicians, so you know that if you know an analytic function near one point, you know it everywhere. And this is completely unphysical, right? In physics, well, you have a freedom to choose initial data and something will happen. So, and depending upon how you choose them, different things will happen. So you can choose data out there and they're not determined by what's happening here. Right? So this theorem is a beautiful result, but it has this analyticity problem, which we don't know how to solve. And that's probably, I would say, one of the most important open problems in this part of mathematical relativity, how to take care of this. And we are in 4 dimensions, and of course you could have a cosmological constant, things become complicated. With higher dimensions, things become complicated, but let me not start discussing this. Now, so this is stationary case. The static is much better understood. So the static is, so what's the difference between stationary and static? Stationary is something which doesn't change in time. And static is something that doesn't change in time. Plus, if you change the time arrow, it doesn't change either. So think about an object which rotates. If you change the arrow of time, it's going to rotate in a different direction. It's not the same configuration. So essentially, static, you can think of saying, well, time independent and not rotating. But not rotating is not assumed. You're just assuming static, and there is a very precise mathematical statement how to do this. And now this theorem is clean, right? So here, static, electrovacuum, regular is Schwarzschild in vacuum. Okay? So this one is much better. Let me just tell you in the 3 minutes proofs, right? So in the stationary, the way to prove this.
So, wait, so if you flip the time arrow, it will still not change?
It will still be time independent, but it rotates in a different direction if it's rotating, right? And static will be the same. So I flip the time arrow, you see the same thing. Right? So that's static. Schwarzschild is static, Kerr is stationary but not static because it rotates, so changing time duration. MP is Majumdar-Papapetrou, or N is Reisner-Nordstrom. Yeah, so there are a finite number of parameters sitting there. You can just describe exactly all the solutions by a finite number of parameters here. Majumdar-Papapetrou is not connected. Right? So several black holes, right? So here I drop the connectedness, then you're going to get Majumdar-Papapetrou. And you drop analytic, you don't need it here. So this is a clean physical theorem that we'd like to have. This one is a dirty one with this good. So to just tell you how things work here. So what when you want to prove uniqueness of stationary black holes, there is a PD identity. You boil it down to a PD problem. And there is a fantastic identity discovered independently by these two gentlemen. And you use this identity to show uniqueness. But now to boil down to a PDE problem, there is a lot of work. And the work is about the topology of your solutions, about existence of so-called null orbits of the generators of the isometry group. You need global coordinate systems to write a PDE identity. You need boundary conditions for this PDE identity. You need to analyze borderline cases as well. So all this work here, the key of the proof is Banting and Mazur, and all these preliminary steps. That's some work I did with Mr. Costa Lopez or with Sudarsky and Wald to get it down to this identity. Static. Well, again, you use, the idea is very clever. You take two black hole solutions and you double them across the event horizons. That's something invented by Banting and Masoud Alam in vacuum and by gentleman Rubak in electrovacuum. So once you have this, again, you write a PDE identity and continue from there. And again, here, my contribution here is just to show that you can solve all these problems which arise here so that you can get to the setting where they arise, right? So if I had to write down the theorems based on just what they did, there'll be 20 hypotheses more, okay? So just cross out many hypotheses. And so if you want to learn more about this, well, you can start with this book, and I'm teaching a course in Tsinghua right now based on this book. And then you can continue with my book on black holes. And once, if you don't have enough, then there is this Living Reviews paper, which just gives the proof of what I said. Good. So this is my contribution to black holes. And so now let me just tell you what Lorentzian metrics are good for and what is this field, right? So first, we're working with Lorentzian metrics. Everyone here knows what a metric is. Lorentzian metric is something like a metric, but not quite. You're going to see a picture shortly. The point of these Lorentzian metrics is that first you use them to determine motion. That's how we calculate how black holes move, how objects move in general relativity. We use the Lorentzian metric for this. And it determines causality. So causality is the thing which tells you there's a black hole here because there's an event horizon and we cannot see through this. And all this is done by a symmetric tensor, which has the property that that the length of a vector can be negative. So that's a Lorentzian metric. It allows for a one dimension in which the lengths can be negative, and otherwise it's like a metric. So a lot of things you can do in Riemannian geometry, you can repeat here, but you have to be careful about these null directions. And so if you take a curve, you're going to say that this curve is time-like, and time-like curves is curves in space-time on which physical objects which have mass move. Okay, that's how this fits with how this mathematical model fits with physics. So a time-like curve, you take a curve, you take its tangent, you take this funny metric, calculate the length of this tangent. If it's negative, you say that this is time-like, and this corresponds to moving slower than light. So moving with velocities which are inside this cone, and so this means that you're moving slower than light. A curve is null when its tangent is 0, but it's not 0 itself. And this corresponds to how light propagates, how photons propagate, how gravitons propagate. Yeah, what else is massless in our universe? Photons, gravitons, it's about it, right? Everything else has mass by one way or another. Say it again. Okay. And yeah, and maybe some neutrinos are massless, but that's not, yeah. It's known now they're massive because I know that there is a mass. Okay, good. So even neutrinos have mass. Good. So these null curves are curves on which light moves or gravitons, so gravitational waves. A curve is causal if it's either time-like or null, right? So you can move with. So that's how signals propagate. They can move slower than light, or maybe at the speed of light, but not faster. And they're space-like. Okay, so that's what the metric does to you. Tells you about causality, and the geodesics of this metric tells you about motions of particles. So this is how light moves. If you have a black hole sitting 600 kilometers from the Earth in the galactical plane, it's going to deform what you see. The mechanism is very simple, right? So you have a curved space-time, so you draw this null geodesic, and actually, if you're looking at a given direction, if you were in flat space-time, you would think that this object is here, but because there is a sun here, then the trajectory is curved, and you look at this direction, but you're seeing something which is actually, in this case, behind the sun. And that's how what happens with the galactical plane if you had a black hole sitting there. So let me show you how this would work if we are traveling, or, well, either we're traveling towards this black hole or this black hole is moving towards us, right? So that so you have this funny effect of rotating things behind, because we're not, if we are moving quite directly in the direction of the center, that wouldn't happen. But if we're a little off, the angle changes and the image gets deformed so that you have the impression of having this rotation here, right? So a very big black hole moving towards us, or sitting in the plane of the galaxy, and we are falling into it, right? This is Schwarzschild, right? So it will be slightly different if this was scalar, right? So that's how, this is about null geodesics. That's how light moves on null geodesics in our model. If you want more simulation. Now, this looked like science fiction, but in fact, this effect of measuring how light is deflected by a black hole, that was the object of this experiment, where people were looking in the sky and tried to see if dark matter, which is something which we don't know what it is, could it possibly be formed by black holes? Now, if that were be the case, then there will be a lot of black holes sitting around us here. Then that would be, this is a expected image of what one should see in the sky. So you look at the light curves of stars, and you see this very specific way the light travels around a black hole. You're going to detect it on the light curve of the stars sitting in the galactic plane. And this is what we should have seen if dark matter was composed with primordial black holes, and this is what they saw. Right? So this is just by looking at the curves, the light curves, and the model that I showed you, allows us to prove that dark matter cannot be composed of.
What was this 600 kilometers?
It was just. That's what you would see if that was the distance, right? So of course, if you have a black hole of 10 solar masses 600 kilometers away from you, you'll need quite a big acceleration not to fall into it. But this is, take black hole 10M, 600 kilometers from us, put the galactic plane behind. This is the simulation. So that's the scales. So of course, the picture, the Ogle experiment assumes we will quite different scales, but the mechanism is this. That's probably what they do at that, right? But I mean, so the hypothesis that most of dark matter would be coming from primordial black holes is certainly falsified. So now what are the exact numbers? I can't tell you. Good. So what next, right? So my field, gravitational waves, right? So you can also see gravitational waves. That's what our theory tells us. And this is a simulation based on actual data. So, so this is a signal of gravitational wave that has been seen in a very specific collision of black holes, well, which is interpreted as a very specific collision of black holes. In other words, this animation here, you can, the gravitational wave that you follow here can be explained by this system of two black holes colliding. And this is what we saw, and that's the interpretation of the event. So black holes are there to stay, and you can actually hear them coalesce. So because the frequencies you've seen here are actually audible frequencies. So if you have two black holes of this kind of masses coalescing, well, let me just play the second largest, longest. So if you hear a noise like that, you can think, aha, maybe some black holes collided somewhere. You're unlikely to hear this as coming from black holes because the signal is very weak. But well, the frequency, the frequency that you hear is actually double of the frequency of the system. No, this is the real. This is what you would just exactly hear for this event. Right. If you amplified by many orders of magnitude gravitational wave and translated it into sound waves. No, right, amplitude, right? So this is exactly the frequency. And this is what you would hear when you have two black holes which with either without spin or with spins aligned with each other. And it's much more interesting if they have spinning and there is spin precession, right? Because then the dynamics is much more complicated. Okay, so this is like a car that has several gears, and eventually the gearbox explodes. So this is again exactly the frequency, right, of what you would hear, So all these things are done by these gravitational wave observatories. The longest running ones are LIGO, so laser interferometric gravitational observatory. Because of Mr. Trump, it's not clear what's going to happen with these instruments. They still have funding for a next year or two, but then everything is open. There is actually several now. The LIGO instrument in the US has been joined by an instrument in Europe called Virgo near Pisa, Italy. GO600 is a prototype which is not measuring things, but really there for the science.
Can I ask a question? So if I have two black holes, if their sizes are not equal to each other, definitely when they come close to each other, they will rotate around each other, right? They would be rotated. Am I right? The only way
well,
that they
I mean, even it's irrespective of size, right? I mean, even if a small one hits a big one, it's going to give some rotation.
If they are exactly same size, they can just collide without any rotation. Am I right?
Even if they have different size,
no rotation.
They can collide head on. Yeah. But it's not probable. Right?
Why?
Because
that's my question.
Hitting head on means that you have to have zero angular momentum relatively, right? So that's a zero measure event in the set of all angular momenta. Of course, so head on is completely unlikely.
I see. Okay.
So here you have at least three real instruments, a fourth one which is just for testing things. In fact, the Japanese one is online now, I think. So we have 1, 2, 3, 4 experiments running. The Australian one has been cancelled, so this will not happen. But it's replaced by an instrument in India, which will start taking data. And you want to have many instruments because this allows you to localize where the wave is coming from. The wave, when the wave hits, suppose this is my plane of observation, the maximum effect would be when the wave hits orthogonally, and if it hits like that, it's going to be minimum effect, right? So if you have several instruments, by comparing the intensities, you can just locate the direction where the wave is coming from. So out of this, 3 years ago, we saw about 100 black hole mergers through gravitational waves. Each black hole, well, actually, we saw about 30 black hole mergers, but each merger gives us 3 black holes for the price of 1. Because when a merger happens, you have 2 black holes which collide, and a third one at the end. So that's the population of black holes we had about 2 years ago. The scale here is the mass of the black hole. So the biggest one here was about 200 solar masses. And the picture this year, we now have about 100 events, and so about 300 black holes. You get, for one observation gives you 3 black holes. Right, exactly, right, yeah. And the mass is, so here you see, right? So this one is the final mass, and it's coming from the merger of these 2 things, yeah, right? So this one is the final mass, and it's coming from the merger of these 2, right? So that's how we have this rather impressive amount of. Say it again. Well, the short run we will have nothing because Trump will shut down the instruments. No, not necessarily, because there's no reason for, if you have 2 black holes traveling in different directions, so there's no, they don't have, if there is another sign. So the current, there is no evidence that there is non-trivial topology of the universe in the data, right? Of course, if you people have tried to look for this, right? So the best model for the universe is spatially flat. So of course, spatially flat, you could make a torus out of it, and people have been trying to see if there's any evidence of toroidal topology, and there is none so far. So there's no reason to assume that there is non-trivial topology. But of course, as you're saying, they could meet, but no, they don't have to. Yeah.
This is quite energy black holes, but black holes cannot split. So all the black holes of the universe are here from the beginning of time.
And to stay. No. They can merge. They can arise. Right? They can, but they cannot split. Right? Yeah. That's a property probably due to Hawking at the end, right? So the famous area theorem, to which I have contributed, by the way, because Hawking proved the area theorem assuming that the horizon is twice differentiable, but there is no reason for that. And so we put in the machinery of geometric measure theory to show that the area theorem holds for any horizons. So yeah. Now I wanted to show you how much progress there has been with these observatories. This is the first wave detected. So you see that the signal here is way slower than the noise, and in the last stage actually becomes louder than the noise. Now a wave seen this January. So GW gravitational wave 150914. This means observed into September 14, 2015. Well, a wave seen in January this year. That's what the noise to to signal ratio is. So all these things. When you saw the first wave, you could think, well, is this really true? Are these waves? Is this some kind of garbage coming from the instruments? I mean, these things are extremely small effects, right? But everything tends to prove that our interpretation is right and that general relativity is the right model for this. Good. So this is general relativity and the equations, right? We're mathematicians. We don't want to see movies, but we want to do something. We want to explain these movies. So these are the Einstein equations. Ricci tensor, Ricci scalar, this is this famous metric, and these are sources of the equations. This is how it looks like if you want to write down the equations, and you never want to write them in this form, but if you wanted to, the Ricci tensor, so that's the object appearing here, then this is this second order differential operator acting on this matrix, right? So this is first derivative of the Lorentzian metric. Each time you have repeated indices, you have a summation, which means that if you look at the number of summations here, you have hundreds of terms, even in dimension, well, order of hundreds, say dimension 4, and of course it goes with dimension. So you have to differentiate once, differentiate twice, obviously something not very nice to work with, and something nonlinear. The Ricci scalar, this is the object which appears here. This is another contraction. So understanding these equations, you just don't write them down and sit down and do it, but you have to do a lot of clever things with him. You wanted to stop me, did you?
You have
the question?
no more than 5 minutes.
Okay, good. So these are the equations. So last thing I'm going to show you probably is that how a complicated evolution with these equations can be. And so this one usually takes a while to start. So let me explain you what we're seeing here. And I probably stops shortly. So let's see view loop. But it's still not running. Okay, good. Good. So let's see. Here, this is a Lorentzian metric. It's actually well, so you see it's Lorentzian because it has a minus here and has 3 pluses. So a real metric would have 4 pluses here. It's particularly simple. These sigmas are just invariant one forms on a sphere. You don't care about what they are. when you write a metric like that, all Einstein equations will become a dynamical system. A dynamical system in these variables A, B, C, and D. Okay, so the whole problem reduced to study this dynamical system. And what you see on this animation is on this axis here, you take the ratio of the function C over the function B. Right? So the ratio of these two functions is telling you how the distances in one direction change with respect to the distances in the other direction. Right? So if C over B becomes big, means that this direction becomes longer compared to this one, and becomes small, then this one becomes longer compared to this one. Right? So this is one axis. And the other one is the ratio over D over B, right? So one is the ratio of these two distances, and the other is the ratio of these two distances, okay? And you see this is a rather complicated behavior. It's supposed to be chaotic. That's an open problem for dynamical system people. I wouldn't give this to a PhD student, but certainly, well, why not? A very good one. So what we know about this is then this theorem by DTO that this behavior is correct for a large class of metrics in this class. What one would like to have is a complete description that's missing. So if you're interested in dynamical systems, go for it. These are called Bianchi 9 cosmologies. This is the hypothesis that this billiard on the triangle gives you the asymptotic behavior of the solutions of this dynamical system. Go for it. Good. I think he has an open set and open non-zero and open should be probably positive measure. Yeah, right. Yeah. So he has an open set, but it's not full measure. Yeah. So there's quite a bit of work to do, and that's it. So I think I'll probably just stop here. Thank you.
Okay, questions?
You mentioned in the beginning your classification results for the
Black holes.
in particular this Kerr solution. So this Kerr solution, it has killing fields and more than one killing field. So in your proof, do you first prove that there's additional killing field and then derive the PDE equations, or the other way around? So
right, no, right. So it's a very long story, because so essentially, first you have to understand all these things I told you about, topology and asymptotic behavior and things like that. Then what you do is you prove that there is a candidate killing vector on the horizon. And this is the original proof is due to Hawking, with many improvements since. And then you use analyticity to extend it off the to Hay spacetime. That's why you have this analyticity. So
where does the PDE come in?
And once you have that, you know that there are two killing vectors, and you do a little work to show, well, quite a bit of work to show that there is a global coordinate system in which you can write down a PDE because you have these two killing vectors. And then
I think I know the story when you start with the two killing vectors, but
but you have to get there. You have to get there. And analyticity is needed to go from the horizon to the space-time, and that's the big open problem.
Thank you very much.
So what happens if you go out of this open set you just mentioned? Are there any simulations?
No, I mean, we think that's correct, right? The picture is correct. But, this system, this billiard has periodic solutions. You can't have a periodic solution with a gravitational field, because moving gravitational objects radiate. So there's no way you could have a periodic one. So certainly this it cannot be true that for every billiard orbit there will be right, and so and understanding this is extremely difficult.
So it's a billiard problem with friction.
Well, that would be no. Well, friction would be too easy, right? Because friction would actually make things settle down.
But
Well, this doesn't
cannot
settle
have,
down.
You said you cannot have periodicity because the black holes decay away. That's why you don't have. Isn't
Right.
it the same as adding friction to the table? No.
No, no. So I mean, yeah, I don't. Yeah, you cannot answer it as simply. But I mean, you can naively exclude some solutions like that. But you're right that you think about it, then maybe these things shouldn't even exist, right? Because but they do. Right? So yeah.
More questions.
There is a right. So there is a big theorem of Ringström which says that every such orbit has a non-trivial omega limit set on a boundary of the phase space. And but this is just proving this is a bit of work, and from this to go to this picture is yet another.
More questions? Sebastian?
Yeah, I have a very, very naive question. Can we decide whether we are in a black hole, our universe?
No, maybe we are. Right.
It's possible.
Yeah. No, because so black hole is a global construct. The definition of an event horizon means well, there must be a region in your space-time which you call the exterior world, and you cannot see beyond the event horizon. So we might very well be in an event horizon of somebody else. Yeah. Right? Yeah, we can. Yeah, we can be in many horizons out there.
More questions? We have 3 minutes. So these gravitational waves move with the speed of light?
Right. Yeah. That's and this can be tested by. In fact, when you there was a very famous gravitational wave event where you could see both the same event with Maxwell, so with light and with gravitational waves, and the speed of arrival was actually not. They didn't arrive at the same time. For a very simple reason. Then when you have a star which explodes, gravitational waves from the center of the star go through without seeing any problem, without being slowed down by matter, while light does. Mm-hmm. So the explosion in the center of this event was, as far as light was concerned, light arrived to the surface of the star with a delay compared to the gravitational waves, and therefore we got a delay between the signals, which is compatible with the hypothesis that the speed of light is exactly the same as the speed of gravitational waves, and giving us, therefore, information about the structure of the explosion.
They also, similar to light, they curve up around other black holes. The gravitational wave of one curves up around.
These geodesics, the light, the gravitons will follow the same geodesics.
I see. Questions? If not, let's thank Piotr again.
Thank you.